So this screencast is going to cover Graham's law and the deviations from the ideal gas law. So recall that in class we looked at diffusion, which is the gradual mixing of two gases by virtue of their kinetic properties. We looked at that in this situation. We had a straw, and in that straw we placed two Q-tips. And the Q-tips were each soaked in a reactant. The reactant in one Q-tip was hydrochloric acid. And remember, the vapor from that will start to diffuse. And then the other one, we had ammonium hydroxide, concentrated in both cases, and the vapor from that would start to diffuse. Based on what we learned about the speed of the molecules of a gas, we know that velocity is proportional to 1 over the molecular weight. And remember that velocity is the rate at which the gas will diffuse, or the rate at which the particles will move. So I asked the question, where is the cloudy result of this reaction if we take hydrochloric acid plus ammonium hydroxide, which are both colorless gases? We end up with a cloudy gas, which in this case would be ammonium chloride and water. We end up with ammonium chloride, the cloudy gas. And I asked, which side would that form on? Recall that the molecular weight, the bigger it is, the slower the particles are going to travel. So we would anticipate that the molecule with the largest molecular weight would be the one that would be slowest, and therefore the reaction would happen closer to that one. So looking at hydrochloric acid, we have hydrogen and chlorine, which have a molecular weight of 36.458. And then we have ammonium chloride, which is 14, and then Cl, which is ammonium hydroxide. What am I talking about? Ammonium hydroxide, which gives us a molecular weight of about 105. So we can see clearly that ammonium hydroxide is going to be the heavier molecule, and therefore we would expect the cloudy ring to happen somewhere on this half of the tube, and that's what most of you found in the lab. It turns out that we can sort of take all of this information and find that the rate of diffusion of one gas divided by the rate of diffusion of another gas is equal to their molecular weights. Notice it's molecular weight 2 over molecular weight 1. This equation right here, that you don't need to memorize, but you need to understand how to use, in the sense that you need to understand the conceptual idea that the heavier gas moves slower, is called Graham's law of diffusion. Now, Graham's law actually applies to another thing that another action that gases can undergo, and that's called effusion. In effusion, we basically have a gas vapor, or just a gas, under pressure, and it is moving from, or escaping from one container into another by a small opening. And effusion, the rate of effusion, follows Graham's law. So if we want to look at effusion, I want to show you a demonstration of what that might look like. So this is a PhET simulation that's showing gases moving around. What I want to do is reset this whole thing. And you'll notice that I have a chamber here. There's a little guy pushing on it. I don't know what he does. I think you can move him up and down. But anyway, I've got a chamber here. This is the temperature. We show the pressure. This pump will add gases. We have a heavy species and a light species. And I've got a lid that I can open and close on this simulation. So I'm going to make sure, start out with it closed. I'm going to add in 100 maybe faster than that. 100 particles of the heavy species, and I'm going to add in 100 particles of the light species. It's good to go. So you can see the heavy species and the light species moving around inside, and you can see the pressure is 0.98 atmospheres. Now, if I open the container, we want to look at the rate of diffusion. So we've got one container, which is our chamber here, that's under pressure, and I'm going to open the lid. I want to do that about 2 millimeters. So let me take a look at the ruler here. I don't know where my ruler went. Well, I'm just going to open it. All right, so I'm going to open this container, and I want you to watch at the rate of diffusion. You can do that by watching up at the top these gas properties up here. You'll see it'll tell you the number of each species that there are, and watch, make a prediction which one you think is going to effuse or move out quicker. So watching the light species and the heavy species, you'll see that the number of light species is going down faster than the number of heavy species. This is because Graham's law of diffusion and Graham's law of effusion follow the same rule. The heavier the molecule of the gas is, the slower it moves. So you'll notice that the light species, or the little red ones, are moving out of the pressurized container much faster than the heavy species. So like I said, diffusion follows that same rule. The heavier the molecule is, the slower it will move. All right, so an example problem that I'd like you to try with this has to do with 4 balloons. And here is the problem. You have 4 balloons. One is filled with carbon dioxide. One is filled with oxygen. One is filled with helium. One with nitrogen gas. And one with methane gas. Okay, these balloons all have a volume. They have a constant volume. Well, they have the same volume. Each of them has the same volume. The temperature is 25 degrees Celsius, and they each have a pressure of 1.0 atmospheres initially with the pure gases. So a couple of questions. First, which balloon has the greatest mass? So that's the first question I want you to answer for class tomorrow. The second question is I want you to compare the average kinetic energies of the molecules. So rank them essentially, which one has the fastest or the greatest kinetic energy, which one has the least. And the final thing is that after 12 hours, all the balloons have decreased in size because there are pores in latex balloons. These balloons have small molecular-sized holes in them, and the gases can escape. My question is, 12 hours later, which balloon will be the smallest? So think about that. Think about the laws of diffusion, effusion, and all the things we talked about in class related to the energy of the gas molecules and their speed to answer this question. Let's talk now about deviations from ideal behavior. So we know that gases are not really all ideal. They don't follow the gas law exactly. But the real question we want to answer is under what circumstances will they most likely exhibit non-ideal behavior? So we're really looking at what are those circumstances under which gases will behave as real gases, not as ideal gases. And I want to talk about those conditions or those circumstances right now. All right, so I want to show you a graph. And this is a graph, as you can see, of PV over RT with as a function of pressure. It's a relationship between PV over RT and the pressure. You'll notice that this dashed line right here represents the ideal gas. So PV over RT, if you remember from the ideal gas law, is equal to N. So for 1 mole of gas, you can see that PV over RT is a constant for an ideal gas, always. For real gases, though, this isn't always true. Look that they all converge on 1 over here, but you can see, for example, for nitrogen, that that number drops below 1 and scoops back up to 1, okay? So for real gases, PV over RT equaling that constant is only true at very low pressures. Now, you should be able to sort of reason through why that is. Remember that when we talked about kinetic molecular theory, one of the assumptions we made is that gases are very spread apart, okay? And the attractive forces between them are very low. However, as we increase the pressure on a real gas, remember that as we increase the pressure, the density, the number density of molecules per unit volume is going to go up, and the molecules are closer together, or they interact more. And when that interaction happens, the intermolecular forces, the attractive forces between those two molecules, will come into play. So the attractive forces, as we increase pressure, the density goes up and the molecules interact more frequently. The attractive forces are no longer negligible. They're significant enough to have an effect on motion. Okay? So gases that will deviate from ideal behavior are those that will have interactions at the strongest intermolecular forces between them. Okay, so if we look at this and we wonder which one would deviate most from, ideal behavior, we have to think about the intermolecular forces between these. And we'll get more into those intermolecular forces, but remember that particles will interact. The intermolecular forces include London dispersion forces, van der Waals forces, and polar molecules interacting. So if we look at this one, we have the potential for some increased London dispersion forces. But we'll come back to that when we talk about IMFs. Now if we look at temperature. So temperature is another circumstance that can change the ideal behavior, have a gas deviate from ideal behavior. If we lower temperature, what happens? So think about that for a second. What happens as we lower temperature? Well, one of the things that happens is that the volume will decrease. Oh, sorry, the velocity. Silly me. All right. The velocity will decrease, right? We know that temperature is proportional to velocity. So as we lower the temperature, the velocity is decreasing. At that point, when the velocity gets low enough, the molecules aren't moving fast enough for those attractive forces to be negligible, right? As they move slower, think about if you threw two magnets past each other, right? When you throw two magnets past each other, they often don't interact, really. But if they're moving pretty slow, if you slowly move another magnet by a magnet, you'll notice that electromagnetic interaction. Same thing happens with molecules. When they're moving really fast, they're just not near each other long enough for that force to act. But when they're moving slow, the attractive forces between the molecules have more of an effect. So the way we show this, these deviations mathematically, is using an equation called the van der Waals equation. And this equation makes corrections to the ideal gas law for real gases. It is not important that you know how to use this equation, but just that you understand where these corrections come from. Okay, so this equation looks like this. P plus AN squared, where N is the number of moles, over V squared for volume, times V minus N, number of moles again, B, and I'll talk about what A and B are in just a second, equals nRT. So notice we have PV equals nRT, but the P and the V have been corrected slightly. Where this part comes from is that the pressure of an ideal gas is equal to the pressure of the real gas plus a factor, a constant, times the number of moles over the volume squared. Okay? That A comes from the idea that the intermolecular forces that cause non-ideal behavior depend on proximity. Okay, so as the frequency of those encounters between the molecules increase, they increase with the square of n per unit volume, i.e. density, right? So we talked about today how this is kind of related to density. The higher the density, the more those interactions happen. So that A tells us about the proximity. And that number is measured. It's different for different gases, and if you were ever to use it, you would be given a table of what that correction factor is. Where the volume comes from is a little easier to understand. N times B really tells us about the volume of the gas molecule. Recall that we talked about how in the kinetic molecular theory, we assume that the molecule is zero, the volume of the molecule is zero. That's not really true. Actual gases, particles of those gases, have volumes. So N times B, the number of moles, times this correction factor B, tells us about the volume. B is very closely related to the size of the particle. So B can kind of tell you the size. A will kind of tell you about the strength of the attractions between them. Just know that these two corrections in real gases have to do with the number of interactions and that force, based on the fact that when we increase the pressure, it doesn't remain ideal. And so we have ideal gases at very low pressures. And when we are looking at temperature and volume, we have to correct for the fact that molecules of gas actually have size. So this equation just kind of gets at that idea that ideal behavior will change, right? We'll deviate from ideal behavior in two circumstances. The first is when we'll adhere to ideal behavior when the pressure is low, because the gas is spread out so it can't interact, and when the temperature is high. So we have ideal gases when the pressure is low and the temperature is high. Remember, the temperature being high has to do with the speed. If it's moving fast, it doesn't have time to interact, and those IMFs can't happen. So intermolecular forces are negligible when the pressure is low and the temperature is high, and then we get an ideal gas. We'll deviate anytime pressure is high or temperature is low.